Welcome to all of you for the conference opening of iiWAS MoMM Show 2021. I wish again that we have been able to meet in person, but unfortunately the situation still doesn't allow us to do so. Actually, you probably heard from the news, Austria is currently pretty much affected by the COVID virus, and the numbers are very bad currently, which resulted in another full lockdown that we currently have in Austria. We are allowed to go to work, which means we can host actually this meeting, so we didn't have to cancel this conference, but of course we are very limited in our actions that we can make. So the only things we're allowed to do is go to work and buy food and things that are necessary for your daily life, but otherwise everything is closed and people are advised to stay at home and to not stay connected. We all wish that we can stay or can become connected again in the next year, and we definitely will continue our conference series of iiWAS MoMM Show 2021. So I would already announce now that in the closing session of this year's conference, we are optimistically going to announce a physical place for iiWAS MoMM Show 2022. So if you're curious on where to hopefully go next year, please join the closing session where there will also be the best paper awards given. This brings me immediately to the program outline. That would be the first thing that I would like to show to you. We have a 3-day conference on Monday, Tuesday, and Wednesday. And the conference will run from 9 a.m. to 6 p.m. on Monday and Tuesday in the Central European time zone, and on 9 a.m. up to 12:30 p.m. on Wednesday, again in the European time zone. We do understand that this is not convenient for all the participants, so some of you have to get up very early or have to stay up very late, or even both. But this is one of the disadvantages of virtual conferences, and we are still doing research on how to improve this and how to create new conference formats, hybrid formats that hopefully will allow us a better interaction in the future, and that will definitely change the way how we work together and how we do our conferences. So talking about this year's program, whenever we have paper sessions, those will be arranged in 3 parallel tracks. And in the program, you will find the link to each of those tracks, and the links stay persistent over the whole 3 days of the conference. The same is true for all the plenary events. We have the plenary now, which is the opening followed by a keynote, and we have a plenary in the afternoon and the World ABC Forum today and tomorrow in the evening, again, Central European time, and the closing session. So for attending the plenaries, there's also a link that is provided to you in the program. Talking about the keynotes, I'm very pleased to welcome and introduce Gill Dobbie. She will be talking about machine learning in healthcare. She's a professor in the School of Computer Science at the University of Auckland, New Zealand, and will be introduced later on for giving her keynote. So for the moment, a big applause to Gill, and thank you for joining us and delivering a keynote at the conference. Our second speaker is Won Kim. He is a distinguished professor and II Vice President of Gachon University near Seoul in Korea. And he's going to talk about AI big data convergence. And his talk will be held this afternoon starting at 3 p.m., followed by the ABC World Forum, which is the 3rd plenary event that we have prepared. For the World ABC Forum, we would like to bring together the fields, the disciplines of AI and big data, and discuss the current trends. And we have very renowned experts in the field talking about this. These are the 2 organizers, Won Kim and Woong Ki Lo, as well as the speakers, Chia-Wai Han, Jaideep Srivastava, Kyung-In Min, Michael J. Carey, Eliza Bettino, Yong-Yu Jung, and Jian Pei. I would like to thank all of those for their valuable contributions to the ABC Forum, and I truly hope for lively discussions in this workshop. This is a new format that we are trying in the conference, but I think the topic is very up to date, so I hope that you will enjoy this. Let me say a few things also about the conference organization. It has proven quite successful that when you're not speaker, you turn your video and audio off during the presentations. If you happen to be in a very small group, then maybe the session chair might ask you to turn your video on, but it's definitely always advisable to have your audio turned off if you're not speaking, in order to avoid audio problems in the transmission of the streams. We kindly ask you to use the chat for all kinds of interactions or questions that you would have. This could be either technical questions or questions from an organizational matter, but I would kindly ask you to be as polite and constructive in your chats, in your comments, as you would be in the real world. We have in each session hosts, which belong to the organization team. They will assist you in any technical problems. And in addition to that, we will have the session chairs who will be responsible for steering the overall process of the sessions, introducing the speakers, asking for questions, moderating the questions, as you know from a physical meeting. Talking about the session hosts, the organizers, I would like to briefly introduce to you also the organizing team. So first of all, there are the steering committee members, and again, a big welcome to them and also a big thank you for putting together again an amazing program. Those are Ismail Khalil, the founder of iiWAS, professor at Johannes Kepler University in Linz, Austria, Sofian Chayaputra from Universitas Islam Negeri, Indonesia, and Dirk Draheim from Tallinn University of Technology in Estonia. Thank you for joining and welcome. Our proceedings chair is Matthias Steinbauer, graduate from Johannes Kepler University in Linz, Austria, and he did a tremendous job in putting together the proceedings. And I do know about some problems that some of you experienced in preparing your papers. I truly apologize for that. There is a new production system, a new workflow in place at ACM, which causes, unfortunately, some collywobbles at the beginning, and we are working on our best to improving this situation. A warm welcome to our General Secretary, Hesti Sujana, who is, as usual, the mental mind and also the caretaker of every other problems or obstacles that encounter during the conferences. And thank you very much, Hesti, for your continuing support for iiWAS. Our communications chair is Paul Wiesinger, also from Johannes Kepler University, Linz, Austria. Paul is responsible for all the technical setup and all the technical communications, and he's also responsible for the recording. At that moment, I would like to mention that all the plenary sessions are recorded and will also be live streamed. And by participating in this session, by clicking on the links, you have agreed that you will join also, or will accept to the recording, and you accept those conditions. We have 3 session hosts for the different tracks. Hesti will be also hosting one track, and the other tracks, the plenary, will be hosted by Andrea Salfinger, Manuela Pollack, and Alexander Gindelhumer. And you will notice them also because they have the co-host sign next to their names, or the host sign next to their names. So much with respect to organizational details. And I would like to hand over now to the iiWAS program co-chairs for their presentation about the specific statistics of iiWAS 2021. Please.
So good morning, good afternoon, and good evening. For some people, it's already after in the evening. So first, I would like to thank you all the program committee members that's helping us to create a program for iiWAS 2021, that we have the team of collecting, processing, analyzing, storing data information to support human activity. Compared to the last year, so if I can get the slides forward to the next one, please. So we have slightly down in terms of the submissions. So we have this year have 88 number of papers submitted, but it comes from 32 different countries. So we still have a quite diverse type of papers that we receive from different country in the world. So we quite proud that we still managed to keep that in this current situation. So mainly, but the majority of the papers still come from our colleague in Japan, And we also see the increase of number of papers coming from Germany. We've been seeing this steady increase of the submission from paper from Germany, then followed by the Austria and other countries. And from the point of view of the PC membership, we have 49 PC members from 20 countries, and all the papers this year will manage to be reviewed by at least 2 PC members. So again, I would like to thank you all the PC members for their hard work in producing the selections of papers that we can be proud of. So in this year conference, so we have 16 sessions, consists of full and short paper. And for this year, the acceptance rates for the paper is 55%. I think this number is slightly higher because we actually have a lower number of submissions. But the quality of the paper that we have received is steady, so we have to actually accept in higher percentage than the usual. So again, I'd like to thank all the authors and also the PC member in helping us in making this conference successful. So for all the authors, we'd like to wish you a successful conference and the sharing of ideas and your research work. Thank you. Thank you, Gabby.
Yes, thank you very much, Maria, and also thanks to Eric. And I also would like to express my gratitude to the PC members and the reviews. I do know that it's a tremendous amount of work to do all those reviews, and I think you have put together again an amazing program. So next, we come to Pari Haghighi, the MoMM 2021 chair from Monash University, and also she is going to tell you some key facts and figures about MoMM 2021. Pari, please, may I ask you?
Hello and welcome everyone. I'm so delighted to be again part of iiWAS and MoMM, and we are really looking forward next year to meet you in person. We are really miss our community, everyone. I'm PC chair of MoMM conference. I'm Pari. So now I'm going to present you now a brief overview of the conference statistics. So this year we had about 20 submissions from 11 different countries, and some of the countries, as you see, they had the highest submission, and we are hoping we get more support from you from other countries. As I see, I'm from Australia, and I see Australia and Japan still having the highest submission. And this year we had the I think the highest kind of review of the papers, because we had like up to 5 reviews for 45% of paper and 3 or 4 reviews for almost 50% of the papers. And for that, we are so grateful to our PC members. We had 47 PC members from 21 countries across the globe. So really, we appreciate their hard work and their time. Next slide, please. So this year, MoMM's theme stays as last year, which is designing and developing innovative mobile and ubiquitous solutions to advance interactive experiences and social good. So this year we have 4 sessions for MoMM. Today we have 2 sessions with 5 papers. Tomorrow afternoon we have 1 session with 5 papers, and Wednesday we have morning session with 4 papers. That's all from me, and we are looking forward to see you in these sessions, hopefully. Thank you, and I hand over back to Gabby.
Yes, Paris, thank you very much. And also thank you for your continuous support to MoMM. I think although the numbers this year are a little bit smaller, it's again, very, very interesting papers that have been put together. And you can already see from the session titles that the topics are really up to date. So I'm sure there will be lively and active discussions. And again, thanks to all the authors and all the reviewers. This already brings me to the end of this opening session. I would like to express my thanks again to all the conference chairs who contributed in shaping this year's iiWAS and MoMM. I would like to thank again all the PC members and reviewers for their good job in selecting the papers, in giving feedback, in giving valuable feedbacks to the authors. I think this is very important in our scientific community, that we really provide creative, productive feedback, so that also those authors of papers who are unfortunately rejected this year can improve and can submit better papers the next year. I would like to thank all the authors and participants of this year's conference, and of course the organizing team of iiWAS and JKU, my co-workers who did a tremendous job. And as usual, my last words are as following. If there is anything that you will like about this year's iiWAS and MoMM, then the thanks go to my great team. And if there's anything that you would like to blame, then please blame this on me. I take all the responsibility for everything that is going wrong. Thank you very much. And I'm going to hand over now again to Pari, because we will continue now with the keynote, but actually I think it's better if we wait for 9:30 to start the keynote. So there will be now a short break of 12 minutes. This means you can enjoy your coffee. Unfortunately, we cannot provide you with coffee remotely, but I think it's better if we continue sharply at 9:30 with the keynote, because some participants might join via other channels who did not participate in the opening, and so we need to adhere to a strict timeline. This closes the opening. Please use the chat if you would like to exchange some conversations, and otherwise I wish you a successful conference. See you in a couple of minutes. Thank you very much and goodbye.
Hello, everyone. I want to thank you all for being here today. And it's my great pleasure now to introduce our first keynote speaker, Professor Gill Dobbie. Gill Dobbie is a professor at the School of Computer Science, University of Auckland, New Zealand. Also, she's the director of Auckland ICT Graduate School and the convener of Mathematical and Information Sciences panel of Marston Fund. And Professor Dobbie is the science lead on the Precision-Driven Health Joint Research Partnership, a plant and food science advisory panel member, and she also chairs the science advisory group for plant tech. She's one of the internationally known experts in the area of data management systems, data stream mining, artificial intelligence, and software engineering. And she has over 200 publications internationally peer-reviewed in these research areas. She has made significant contributions to the foundations of database systems. This includes defining a data model for semi-structured data in collaboration with her colleagues at the National University of Singapore. Professor Dobbie's research has been applied across a wide range of domains, including healthcare. That is actually the topic of today's keynote speech, and the title is Machine Learning in Healthcare. Professor Dobbie is going to share with us today I'm going to discuss the gap between novel machine learning methods and their application in society and how we can address that. So without further ado, let's welcome our keynote speaker, Professor Gill Dobbie. Gill, floor is yours. You may start. Thank you.
Thank you very much for the introduction, Pari. I'll try sharing my screen. Okay, so again, Pari, thank you very much for the introduction. It's a great honor to speak at iiWAS and MoMM. And like Gabriele, I'd have preferred to have met all of you in person rather than be speaking from my home. In Auckland, New Zealand, we're still in lockdown. So I'm working from home, and I think I have been for the last 100 or more days. So welcome to my house. So I do have very good memories of iiWAS and MoMM when I attended in the past, and I do look forward to attending again in the future. So in this talk, I will focus on some of the initiatives I've been involved in healthcare in New Zealand. So while the sustainability goals are a strange way to start a machine learning talk, I'd like to point out that we as a community can take action in many of these areas. As Pari pointed out, the areas in which I apply my research are quite broad. So when I look at the UN Sustainability Development Goals, I work in the third goal, good health and well-being, and that's what I'll be further elaborating on in this talk. I also work in the seventh goal, affordable and clean energy. In this area with engineers, we're modelling what alternative power generation sources will bring to the national grid. I work in 10, the reduced inequalities. So with sociologists, we're identifying embedded bias in machine learning algorithms. And I work in 12, which is responsible consumption and production. So this is a particularly important area in New Zealand where we depend a lot on agriculture and horticulture. It's important that we look after our land for future generations. So for this project, along with local bodies and groundwater scientists, we're modelling levels of nitrates in our freshwater waterways. Although this talk that I'm giving today focuses on machine learning and how it can support decision-making in healthcare, I believe that lessons learned from this area can be applied in all these other areas. As we all know, there's a lot of research into novel ways machine learning algorithms can be applied in healthcare. Examples include image analysis, which can be used to find anomalies or to provide accurate measurements of the growth and shrinkage of tumours, for example. Adversarial learning can be used in drug discovery. Operating theatre scheduling is an example of curbing treatment costs. Analysis of healthcare records are used to find relationships between diseases and symptoms. And analysis of healthcare pathways can be used to predict medical diagnoses. NZ has traditionally had a strength in medical research, and this is translated to a strength in the application of machine learning to healthcare in New Zealand. A structured literature review published in BMC Medical Informatics and Decision Making in April 2021 shows the total citations for papers in AI in healthcare. While I do question the study, I would like to highlight that New Zealand is ranked 6th in total citations. So a well-known challenge in translational research is the adoption of results in practice. So in this diagram, we can see that there's research that goes on in the university. There are then barriers and this, what we call a valley of death, before the results from the research lab go into the industry technology transfer. And then there's another valley of death before they're implemented in the clinical setting. So the valleys of death are used to describe situations where studies failed to reach clinical implementation. This first valley, Valley 1, fails to raise funding to commercialise products, and Valley 2 represents barriers to adoption in the healthcare setting. The diagram was originally drawn to represent clinical studies and how difficult it is, or where the challenges are in commercialising and then applying the clinical studies, but it applies equally as well to designing innovative machine learning solutions in healthcare. Gaining traction in the New Zealand healthcare setting is made even more difficult through the complex structure of the health system. In New Zealand, although we're a small country with a small population, we have 20 district health boards. So that's what's shown on this map. Each of the district health boards is likely to be running their own computing infrastructure. There's also no standardized sharing of data between primary health providers, that's the general practitioners, secondary health providers, who are the specialists, and tertiary health providers, who are the hospitals. So as you can see, we're working in quite a complex setting. The one thing that we do have in our favour in New Zealand is an NHI number, or a National Health Index number. So if each individual in New Zealand can be identified by the NHI number, and this obviously helps when we're matching data records. So in this talk, I'm going to be looking at two different approaches to bringing research results into the healthcare sector. The first is through a large partnership, which Pari mentioned in the introduction. And the second is just through small-scale individual projects that I've worked on. I'll start off with the large partnerships. So to overcome the challenge of translational research in New Zealand, we formed a joint research partnership between industry, research institutes, and government. It's a 7-year partnership and has been running for 5 years. I'd like to play a video that introduces the partnership in more detail.
Precision-Driven Health is a 7-year research partnership to improve health outcomes through data science.
So our partnership is between the health IT sector, with Orion Health as the lead vendor there, our health sector, which includes Waitemata District Health Board, and our universities, who have a lot of expertise in data science. So whether that's data about your social circumstances or about information you can collect from devices or something from your genome.
We can build a picture of an individual, and then when I go to the doctor, they actually understand me and my circumstances more and can tailor the care to me. A lot of the information is already available, and we're making it much more available.
So what we're building through our research is the ability to take new data sources, such as the machines that you might be plugged into when you're in hospital, and then also how to engage individual patients with that. So for example, building a chatbot, which is an interactive text system.
Precision-Driven Health puts New Zealand at the forefront of precision medicine, developing data-driven healthcare solutions that can be applied globally.
So the partnership is committed to investing approximately $38 million over the next 6 or 7 years. So how do you take that data and make better decisions with that? So the benefits for this start with the individual, who hopefully can get better health more targeted for them. Secondly, it's our clinicians, who get access to the expertise that others are producing around the world. And thirdly, it's whoever's paying for our healthcare.
The future's really exciting, because at the moment we're only using a tiny amount of the data that's actually available. We'll be able to become much more specific about people's healthcare.
So the criteria for all of the research we do is that there are health benefits to New Zealand and there are commercial opportunities for New Zealand. To try to design the future of health using a lot of data to personalise the treatment that we give to individuals.
So that was just a brief introduction to the Precision Driven Health Project. The video was made for the KiwiNet Awards. Through these awards, we won a section for the Research and Business Partnership. And in this, they acknowledged the difficulty of bringing together the different parties in a partnership. Okay, so now I'd just like to introduce the partnership in a bit more detail. So the mission and the vision of the partnership is ambitious. The mission is to create capability to optimize the health of each individual and their family by combining and learning from all available data. And the reason we want to do this is to improve health outcomes globally, increase health provider efficiency, and enable commercial success. As was pointed out in the video, there are various players in the partnership. So there's the health sector, and they're looking to improve health outcomes in particular and develop and engage staff. There's the commercial sector, and the initial partner there was Orion Health, who's a large software company in New Zealand that specialises in healthcare software. And there was always an understanding that other companies would join the partnership. The university sector was also part of the partnership, initially with the largest university in New Zealand, the University of Auckland. And the driver here was to develop world-leading academic expertise in health and technology. And it was a way to develop and attract and retain researchers. And finally, the government is also a partner in this. A lot of the healthcare in New Zealand is public healthcare. So one of the drivers for the government was to reduce the cost and increase the quality of healthcare with the input of machine learning. And another driver was to build a thriving tech sector in this area. So the projects that are funded by Precision Driven Health are required to benefit research, industry, and healthcare. And each of the projects was expected to fall within one of the themes. So the 4 themes are new data sources, where we're finding and bringing together new data sources that aren't normally integrated, building novel predictive models based on current practice and novel data sets, providing precise and timely healthcare, which could be built on better predictive models and support the decision-making, and finally providing information that will empower patients, looking at how to get information to individuals and their families and how to present that information in a way that they will understand. So through the project, there have been a number of achievements. We've got the standard sorts of measures. So we've funded 50 projects. We've provided 60 student scholarships. We've supported the development of around 10 products and published over 100 peer-reviewed papers. We've also received a number of awards. So the KiwiNet Award was just one of them. I think, though, the main achievements have been these 3 bullet points that I've put in bold at the bottom. The first is that we raised the profile of health data science through research and public outreach events. We've also fostered collaborations between individual researchers, clinicians, and entrepreneurs, and these collaborations are unlikely to have occurred without the partnership in place. We've also led thinking across New Zealand about addressing inequities using machine learning in healthcare. So in New Zealand, we have various groups of people and the healthcare system is not necessarily seen as treating them all equally. So using machine learning, we can highlight some of these inequities. While the partnership has made great advances in New Zealand, there have been challenges along the way. And note, please, that these are my views and not the review of the partnership and not the views of the partnership. So one of the main challenges of the partnership has been alignment. So it's difficult to align the goals of industry, the healthcare sector, and researchers. In general, the goals of industry are to build products to take to market. The goals of the healthcare sector are to care for their patients, and the goals of researchers is to advance the field of machine learning. So finding the sweet spot between all those goals has proved a challenge. Tensions that have arisen have been around what's called research timing. So often with our research, we have students who do our research with us, and those students start their projects at certain times, and that timing doesn't necessarily align to the timing that either industry or the healthcare sector work to. Also, the cost of hiring researchers or working with researchers in New Zealand is quite high because of the overheads that are required. And another challenge has been that advances in healthcare can often be made with known results from machine learning. So the projects may not advance the research per se. So usually in each of the project, 2 of the 3 stakeholders benefited, but it was very rare where we hit the sweet spot where all 3 of the stakeholder groups benefited. A second challenge was adoption. Here we have the valleys of death. So it was generally, we bridged the gap between the results and industry, but we found that it was still difficult to have the outputs of industry adopted in the healthcare sector. So these difficulties arose because in the healthcare sector, there are usually definite pathways, and it was difficult to embed any new tools within those pathways. Also, as I pointed out earlier, we have 20 health boards across New Zealand, and each of them runs their own large computing systems. So again, there is no standard approach, so it's difficult to embed new results when there's no standard approach. There's also a bit of a lack of trust in artificial intelligence and machine learning from both the public and the healthcare system, which results in a lack of confidence in any tools that are built. Okay, so I mentioned that I'd be looking at 2 approaches. So the second approach that I want to consider is small-scale individual projects. And I have a specific focus here on using routinely collected data and machine learning to improve health outcomes. So I've worked in a number of projects that fall into this category. I've worked with an ear, nose and throat specialist building an app to build a better model of an individual. Another project, I've worked with an old age psychiatrist in the diagnosis of mild cognitive impairment. I've also worked with a health physician on a lifestyle checkup for children and teens to improve health outcomes among children in New Zealand. And the final project that I want to mention, which I'll go into in more detail, is work that I've done with a medical physicist on 2 radiography projects. One is predicting when a replan may be necessary, and the other is predicting when the linear accelerator, which delivers radiation, is likely to need recalibration. So I've got another couple of videos from students' projects. The first one explains the project in general, and the second one explains the methodology.
Hello, my name is Shimi. In this video, I'm planning to introduce our powerful project, which is about artificial intelligence and radiotherapy. In my section, I will mainly focus on the project background, the software architecture, and then show a demo of our product. So the first question is, what is radiotherapy? Radiotherapy is a cancer treatment that uses high energy radiation to kill cancer cells and shrink tumors. However, the patient's anatomy and biology can change in size and shape during the course of cancer treatment. Therefore, people introduced the idea of adaptive radiotherapy, which is to use multiple treatment plans to account for these changes so that it can deliver the radiation to the tumor more accurately. This modification of treatment plans can happen throughout the entire process of radiotherapy. Due to the rapid increase in computational power, as well as in data collection and sharing capabilities, a large number of AI techniques, such as deep learning theories and algorithms, have been published in the recent several years. It has the potential to help and improve the clinical decision-making. For example, increase the efficiency for clinical staff, improve the quality of treatment, provide additional clinical information, and also make prediction of treatment response. Therefore, our team decided to integrate the machine learning models into a web application to improve the efficiency of radiotherapy. We're not going to replace the human judgment or generate the exact treatment plan due to the consideration of safety. Based on the requirements from the stakeholders, we will only need to provide suggestions about whether a patient needs a replan or not. The data we received from the Whitehall Hospital include 100 anonymous patients with head and neck cancers. 50 of them had experienced a replanning during their cancer treatment, and the other half of them just received the normal radiotherapy. This diagram shows the high-level architecture of our project. We use React for the front end, and the UI components from end design to provide a consistent experience. The back end is developed in Flex, which is responsible for interacting with our machine learning model, and then send the result back to the front end for easy consumption. This is the user interface that we have for our project. The name of the feature may include some medical terminologies. Therefore, we provide a short description and an indication of what they need to improve for each of them. For example, the message here shows that the user can choose to include multiple stages of cancer. So after we input all the required data, we can click the submit button, and then it will tell us whether the patient needs a replan or not. This is the end of my part. Thanks for watching.
Okay, and the second video is, the second video is the student explaining the methodology that they followed in the project.
Hello, I am Jacinta, and I will be presenting the second half of the project summary video for Project 123, AI and Radiotherapy. First, introducing the model. The data we received was spent to a 70-30 split for training and testing. About the 70-30 for training, we performed a 5-fold cross-validation approach in order to tune the hyperparameters of whatever model we decided to use. We evaluated the resulting model using 3 main metrics: the cross-validation accuracy, test accuracy, and the point score. Our initial model is a decision tree classifier, as a literature review suggests that tree-based classifiers will be the most ideal for our table data. Out of the 130 features provided, the initial model only included the weights and morphology of the patient, the staging of the cancer, and the critical and planning target volumes of the tumor. And also improved the existing model, which had a test accuracy of 66% and an F1 score of 68%. There are two different directions we have explored. Firstly, we can use ensemble learning to attempt to improve the existing decision tree. The other approach we explored is feature engineering. As there are many more features provided, we can attempt to add more features and see if the results improve. In comparing the different classifiers, order rank is used to compare the different classified results, which first uses the fragment test and then the menu test to compare the different classifiers. The resulting CD diagram showed the random forest classifier consistently outperforming other ensemble options, which warrants to switch to random forest being the preferred classifier. For feature engineering, various features were added to the initial features and then evaluated, some of which are shown in this table. While some features improved the cross-validation accuracy, the other evaluation metrics recorded were on average lower than the initial set of features. And it was decided that the original set of features were still the base for the model. Once the classifier and features were decided, the model was trained using the whole dataset, which yielded a cross-validation accuracy of 76.8%. This is a significant improvement to the current prediction methods, which is simply a blind guess based on the experience of the radiotherapy team, and can help improve the efficiency of radiotherapy implant decisions. The limitation of the current model stems mostly from the delay in collecting and sending the data due to the hacking of the Wi-Fi disk health board. Due to the delay, we were only able to get 100 cases instead of the promised 700 to 800 cases initially planned. Additionally, we were not able to utilize the image data as we decided that in a limited time frame, it was more worthwhile to improve the accuracy of the existing model rather than implementing a CNN and incorporating it with the random forest model. Similarly, for future work, utilizing the image data as well as training the model on a much larger dataset would be the logical next steps. Thank you for listening to this video.
Okay, and the second project that I want to introduce in this section is another oncology project. In this project, we were predicting when the linear accelerator or LINAC machine would need recalibration. As you can appreciate, there's already a well-defined maintenance schedule, and the model we produced was only used as an alarm system, and the results were already checked, or always checked, to ensure that they were correct. So in this project, we monitored the outputs of the machines to predict when recalibration would be needed. Okay, we treated it as a typical supervised machine learning problem. We had historic labeled data from one of the LINAC machines. We tried a number of different machine learning algorithms, and we built a model using the most appropriate of those. And from that, we could feed current data in and find out when a machine was going to need recalibration. The training data looked like this. We had various energy sources as our features, and then the labels were these labels that showed pre-adjustment and post-adjustment of the machines. In the end, we chose to use an LSTM to do the model prediction. As you can see in this graph, the blue line is the training, the red line is the real values, and the goldy kind of line is the predictions. So in this diagram, you can see that we were able to predict trends, but not the actual values. So the achievements of the small scale individual projects, I think these 3 bullet points were all very important. So I think through the co-design of the project with the medical physicist, we were able to build trust and understanding of machine learning. the second opportunity was providing the opportunity for our students to carry out applied research on interesting real-world problems. And another achievement was fostering the relationship between the individual researchers and the clinicians. However, we still didn't solve the challenge of these two valleys of death. We didn't take our outputs to industry, and we only went part way to the clinical implementation. So these models, they may be used locally, but they're unlikely to be part of any pathway. And in fact, that's what we've found with a number of the solutions that we have created. Often they'll be created for a particular purpose in a particular hospital. They'll be used and applied in that hospital, but will not be applied more generally. So from all this research, from both the large partnership and the small scale individual projects, what lessons have we learned? So the main lesson, I think, is that co-design is essential. It's not just a nice to have, it's essential that we have a domain expert there that understands the data and also understands the context of the problem and how the data has been generated. Often when I'm working on applied projects like this, I find that domain experts want to jump to what algorithm we should be using. So they may have heard about decision trees or random forests or deep learning, and they want to use what they've heard about. It's quite difficult to slow them down and emphasize that we actually need a good understanding of the problem before we can come up with a solution. We also need a good understanding of the data that's available and the characteristics of that data. And additionally, we need to understand what the expected output should be and what the constraints are on the output, and also who's going to use it. So before you can decide on what algorithm you're going to use, you need to understand all of those things. You also have to understand a little bit about the comfort of patients and clinicians with regards to artificial intelligence and machine learning. If they're uncomfortable, then we obviously need something which is much more explainable so that we can explain what's going on. If they're comfortable, then and they're willing to trust the algorithms, then we can use some of the black box algorithms. Okay. So what conclusions can we draw? It's well known that the cost of transdisciplinary research is high, but from these projects, we can see that it's worth it. We're only scratching the surface of where machine learning can have an impact in healthcare. Co-design with healthcare professionals is essential for understanding the problem, designing fit-for-purpose solutions, and for uptake. There's a lot of data, and it's in various types. So there's a lot of textual data, there's a lot of notes from GPs, there's a lot of images, and there's a lot of semi-structured data. So integrating all these types of data is a challenge. The data is also stored in many different formats, so there's a lot of pre-processing to get it into a suitable format. There's also a lack of understanding around machine learning and AI in general. So there is a need to work with stakeholders to build that understanding and also to build trust. And it's important not to underestimate the overhead of getting a product to market or to a place where it can have impact. And from that regard, it's important to build bridges over the valleys of death. Finally, there's no ethical or regulatory framework in New Zealand around machine learning and healthcare. So industry and government need to get together to work on this so that we're not reinventing the wheel for every project that we undertake in this area. So I think for this conference, it's important to think about what we can do as machine learning researchers to build trust in this area. So in order to build that trust and understanding, it's important, as I've mentioned a few times, to work in co-design with the domain experts. This provides measures of certainty and uncertainty in the predictions. Well, I should say that again, sorry. To build that trust, we can design algorithms which will provide measures of uncertainty and predictions. We need to provide explainability and actionable results, and also describe metrics that make clinical sense. So often the clinicians don't really understand the metrics we use, and we don't understand what they're talking about. So there are real terminology issues that we need to work on. We need methods for transferring models between populations and also for localizing the models for the local populations, and ways of demonstrating that we do not have embedded inequities. Finally, we need to find the best approach to address the translational gaps. I think that this will happen over time to a certain extent, but there's work that we can do in that area as machine learning specialists. So I'd like to finish by thanking my many collaborators. I do work on these projects with others. It's not all my own work. And I'd like to thank the audience here, and I am keen to answer any questions that you have.
Thank you so much, Gill, for the enlightening speech and valuable insights you presented. You highlighted very important, points for those who work in this area, including me. So now first, before I have a few questions, but before I ask one question, I want to ask the audience, if you have any question, you can use the chat to submit your question, or if you like, it's okay if you want to, do it, unmute and ask the question, or either option is okay.
I actually have a question.
Fantastic. Go for it.
Thank you, Gill, for the extraordinary talk. I was very excited listening to you. I have one question. Since you are one of the experts in the field of machine learning in healthcare, how can we build a trustworthy machine learning in the field of healthcare? The difficulty of developing applications for the field of healthcare is the trustworthiness. So how can we build trustworthy machine learning applications in the field of healthcare? Thank you very much.
So Ismail, I guess it depends on how we define trustworthy. So we'd have to be able to define it before we can build such systems. We can't build systems that people are going to trust 100%. I don't believe. So I think that things like explainability and expressing uncertainties will help build trust with people. So I think it's an interesting question. It would be fantastic if we could build something that was 100% trustworthy. But, you know, even the physical machines that are used in healthcare currently are not 100% trustworthy. So we can only do what we can do.
Especially in the field of healthcare.
Yes, yeah.
Because it is more a sensitive issue to trust machine to do the kind of things we used as humans to do than in other fields, for example, e-commerce or some other application domain. Thank you, Jill. Thank you, Jill.
It's an interesting debate to have. Joseph, you have your hand up?
Yes, Joseph has a question. Yes.
Okay, hello, here's Joseph from Johannes Kepler University in Linz. Also from my side, a lot of thanks for this presentation. In particular, I liked also the overview of your program you are involved, which is about whole of the country, New Zealand, and maybe even more. And actually, I have two questions, maybe one question and a remark. The first question is, in the health sector, I was also sometimes involved in some projects in healthcare. We are somehow in the quite good situation that quite some standards are existing. We have these data exchange standards, HL7 or IDE and so on. And my question is, do these standards help for using the data in machine learning or artificial intelligence or data mining or not? Maybe you have some experience or some meaning on that. I made the experience it helped a little bit, but the semantics of the data was not that clearly defined within, because within this field, then you find text and so on. So my first question is this a standard standards related part? And the second question is, in the medical domain, we have this really complicated validation process. Each machinery that is used or is allowed to be used in a hospital must undergo this validation process, and of course also each software. And this is actually the reason that we find in our hospitals quite old devices and even old software systems. And I think this is also a challenge or gap, which also Ismail mentioned. We have, or somebody has to integrate this trust issue, trust concept into these validation processes. Okay, these are my questions and comments. I'm asking for your meaning on that.
Thanks for the question, Joseph. With regards to the standards, HL7, etc., I think that one of the projects that was undertaken in precision-driven health was a natural language processing project. And I think that the standards helped there because they were taking raw text and getting meaning from that raw text and therefore converting things into the standards. So they're probably useful for natural language processing and for transformation of information. I'm not sure how much more widely they're useful than that. And another project that they worked on in precision-driven health was that a lot of the descriptions of medicines were not described in standard ways. And so there was a project there where they standardized the way doses were described. So there's certainly a lot of need for standardization. I don't have enough direct experience to know whether the standards are currently enough or not. With regards to the validation process, I think that this is where I was talking about the regulatory guidelines. So I think there do need to be guidelines that are developed around what is expected and acceptable. And I don't know whether they should be developed on a country by country basis or whether there should be an international standard. Certainly, I don't think we want just any old algorithm or any old model adopted. And another piece of work that I've been doing recently has been in an algorithm hub in New Zealand. So we've been choosing which algorithms to put into this algorithm hub, and we've come up with our own definition of the criteria which they have to satisfy. So it would be very, very useful to have standard guidelines. So they're not real answers.
Yeah, but that's the real world. Yes.
Thank you,
Okay, thank you.
Gill, we have a question in the chat. I'm not sure if you can read it, or would you like me to read it?
I can read it, thanks.
Oh, okay, great.
Yeah. So Michelle, thank you for your question. So you're asking whether there was a role for data and process conceptual models in the projects that I've worked on. So certainly there have been conceptual models. And again, a lot of this has been related to translation. So these are ways of defining, I guess, the translations or the basis on which to define the translations. So they've certainly been quite widely used.
While we are waiting, maybe we have more questions. I ask myself a question. You emphasized how co-design is important, and we know, but with co-design, we see that it's not just, one group. So it's not just clinicians and experts, they are also patients, there are other stakeholders, the organization. So how much you involve patients, in these projects?
Yep. An example of this is the mild cognitive impairment project that I'm working on. And what we're doing there is we're holding forums before we start the project. And this is to understand the comfort of patients and caregivers in the use of artificial intelligence and machine learning in diagnosing mild cognitive impairment and dementia. And there have been a number of studies like that that have been done across New Zealand. Another area where patients are involved is in the user interface design, and there've been quite a few surveys done amongst different groups of people to work out what the best interface is for that particular group. So yeah, patients have been quite involved, and I think that was the thing in precision-driven health, that one of the themes was around empowering patients. So there's no sense in building systems that are not going to be used for various reasons.
Thank you. And in these projects, you know, because most of them required training models, machine learning, deep learning. And based on my experience, I don't know if you had that experience, sometimes there is not sufficient data, or there is data and really needs cleaning. There are lots of missing data, you know, when you get to real health data, you see lots of problems. And if you could tell us about your experience with that as well.
So the last two projects with the medical physicist, we did struggle a lot with data. And as one of the students said, one of the problems there was that the district health board was hacked. And so we ran into extra problems that we didn't expect there. So with that project, we ended up working with the data that we had, and then the guy we were working with, he was able to test the models on real data to prove its efficacy. In other projects, what we've done is we've generated data. So we've built our own agent-based systems. We've taken the original data as a model and built these systems that will generate data, which is similar to the original. So it just, we have different ways of working for different projects, I think.
Thank you. We have a question in the chat, which is about one of the major problems when it comes to health-related data and its data privacy. And yeah, I'm sure you can read it. So if you could please answer them.
Yep. So did we gather information anonymously, or did we treat data as it was? So again, there is in New Zealand, we have to abide by quite strong ethical guidelines. And so every project we apply for ethics approval. The mild cognitive impairment project that I'm currently working on, we will work in a sandbox and not take the data out of the hospital. So we're able to do that. Another project, so some of the other projects that we ensure that there's no identifying information available. So again, it depends on it. It's a project by project thing. For any project where there is likely to be any privacy implications, we apply for ethics approval. And also one of the big projects that we did through precision-driven health was around anonymizing data. So we built software to anonymize data sets.
Great, thank you. Any other questions from audience? If we wanna, you provided great learning lessons, but if we wanna take one important advice to answer the question you had in for today's talk, how to address the gap between novel machine learning methods and their application in the society, what would be?
I think the one piece of advice would be even though there are the gaps, it's really worth doing the research. So there is a large overhead to doing translational research like this, but I think that it will lead to richer results in the machine learning area.
Great. Thank you very much. So I guess, is there any question? No? Okay, so if not, then this ends the keynote speech session. We thank Gill again for her great talk. We are going to have a half an hour break and then resume at 11 a.m. European time. And we're going to have 3 in parallel sessions, 2 iiWAS sessions and 1 session. And please note, every session has its own Zoom link. And we are hoping to see you after the break in these sessions. Thank you, everyone, for joining today. And thank you, Gill, again. I clap on behalf of everyone. Thank you
very much for listening.
Thank you. So this is